Dense retrieval still misses the right chunk when wording drifts. I'll use ColBERT in Python to re-rank candidates with token level matching, so RAG recall improves without stuffing more context. This is the workflow you'll know how to run when we're done, which retrieves candidates and re-ranks them by matching important words to boost recall without larger context windows. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Dense retrieval and simple lexical search each have blind spots. Dense vectors find paraphrases but can blur small but critical words. Lexical search finds exact terms but breaks when users rephrase. ColBERT sits between those two. It keeps token-level signals while still using learned embeddings, so you get token-level matches amplified by semantic similarity. Think of a search result as a pile of candidate passages. The goal is to sort that pile so the most useful passages are at the top for a downstream generator. Success means fewer missed facts in the generated answer, and lower token budgets because you only pass what matters. People reach for ColBERT when they need precision on specific words, like names or numbers, while still tolerating paraphrase. At an intuitive level, ColBERT scores by comparing tokens, not just whole sentences. Each word gets a vector. When you score a passage, you find the closest token match for every query token and sum those top matches. That gives a MaxSim signal. So, if a query says vehicle and a document says automobile, the token vectors still match, and that passage can rise above a literal lexical tie. We will build a tiny pipeline that shows this benefit on a toy corpus. First, we run a minimal ColBERT re-rank over 3 passages and see what it prefers. Then we compare lexical overlap to ColBERT when wording drifts. Next, we expand the pool a little, and then we show how larger pools can reveal a target passage. Finally, we extract a tight RAG context from ColBERT's top results. No heavy math, just the idea and the trades. Then you can scale it. Now we'll run a minimal re-rank. This snippet performs a minimal ColBERT re-rank over a tiny list of 3 passages. The list docs holds short, readable candidates, and the variable query contains a simple user need. The searcher object loads a ColBERT checkpoint that performs late interaction scoring. The call to searcher.rerank takes the query and documents and returns candidates sorted by token-level MaxSim relevance. The variable res captures the ordered results, where each item includes a text and a score. Increasing k changes how many top items are returned, but does not change internal scoring. The printed top passage and score show ColBERT's best match at a glance. Next, we'll craft a query that avoids an exact keyword. This example contrasts a naive lexical overlap with ColBERT on a wording drift. The variable q2 intentionally avoids the word car and uses vehicle and freeway to induce mismatch. The setTalk holds query tokens, and the listLex orders document indices by shared token count with a deterministic tiebreaker. The call searcher.rerank applies ColBERT's late interaction scoring over the same docs, which can align vehicle with automobile, even when tokens differ. The result, C2, holds the ColBERT order. If you increase k, you only change how many ColBERT results you inspect. The print shows which passage lexical overlap prefers versus ColBERT's top, highlighting semantic gains. Now we'll enlarge the pool a little and see how re-ranking picks the best from a candidate bucket. This code builds a slightly larger corpus, selects a small lexical candidate pool, and lets ColBERT refine it. The list corpus extends the original docs with 3 freeway-related passages. The integer k controls how many lexical candidates to pass forward. and order ranks indices by shared token count using Talk2. The list cans collects those candidate texts, and searcher.rerank applies ColBERT's token level MaxSim to produce a stronger semantic order. Increasing K enlarges the candidate set, which can improve recall but costs more re-ranking time. The printed line shows the ColBERT top passage from the candidate pool and the pool size you used. Next, we'll compare small and larger candidate pools to see a recall difference. This snippet shows how enlarging candidate pools can help ColBERT surface better chunks. The string target marks a semantically important cue that might be missed by smaller pools. The lists Order 3 and Order 6 select 3 and 6 lexical candidates, and C3 and C6 hold the corresponding texts. The calls to searcher.rerank re-rank each pool, and the flags f-small and f-big check whether any top results contain the target term. Increasing pool size typically raises recall, but adds computation. The printed booleans reveal whether the stronger passage only appears once the pool is large enough to include it, demonstrating a pragmatic recall win. Finally, we'll build a compact RAG context from ColBERT's top passages. This snippet builds a small but effective RAG context using ColBERT's top K passages. The integer top K controls how many re-ranked results to include, and rFinal holds the ordered ColBERT outputs for Q2 over cans. The variable context concatenates the top text and trims to a compact budget to avoid overstuffing the LLM window. The variable used reflects how many chunks made it into the context, which you can tune to balance recall and cost. Increasing top K expands coverage, but grows the context. The printed length and chunk count confirm a tight, ColBERT-informed context ready for generation. Taken together, this toy pipeline maps to a real system easily. The lexical step can be a fast inverted index or an ANN over sparse vectors. ColBERT then re-ranks a handful of candidates to protect recall on critical tokens. In practice, this lowers the chance that your generator misses an entity or a number without enlarging the whole prompt. Recap: ColBERT is token-aware, late interaction scoring that boosts semantic matches when wording changes. Use it when you need precise recall for important words, but still want semantic flexibility. One caveat: larger candidate pools help recall, but cost more re-rank time. Next step: scale the candidate pool and measure recall versus latency as you grow the corpus. Or add an ANN index for the lexical stage to keep first stage latency low. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.